Hello everyone, welcome to the another session. In this video, I'm going to discuss about the mathematical language to represent the quantum bits. As we know that the quantum bits is one of the fundamental storage or process information in case of quantum computing. In case of qubit point of view, the states, either zero state or the one state, exist in terms of superposition, and this qubit is represented with the combination of all the available states. That representation in general, it is like if one qubit is having two states like zero state and one state. These are the two different states, and the qubit is nothing but is a representation of the superposition of all the available states in that particular system, where alpha and beta are the probability amplitudes. This is the in general representation of qubits. This qubit, in what way we can represent mathematically, that part we are going to discuss here by using the vectors. If you want to represent the mathematically this qubit, these states are described as vectors in a two-dimensional space, in two-dimensional complex vector space, those called as Hilbert space. That part we'll discuss in the another session. As we know that vector space is the representation of the positions of a vector, but here in case of quantum computing we are using the word like Hilbert space. So each and every point is represented in the Hilbert space. Coming to the qubit point of view, this is the general representation of the qubit with the help of superposition principle. Coming to the basic states like zero state and one state, these states are mathematically represented using like vectors. This is represent like 1 0 vector space, and it is state 1 is represent with the 0 1 vector. So 0 state vector is represented with the column matrix like 1 0 in terms of vector space. One state is represented with the 0 1. Wherever if you want to utilize or if you want to replace these states with the help of vectors, we need to replace the state 0 with the 1 0. State 1 is replaced with the 0 1. Therefore, psi alpha state 0 plus beta state 1 can be rewrite as alpha 1 0 beta 0 1 in vector space. Therefore, alpha into 1 alpha 0 plus 0 beta into 0 0 beta into 1 beta, then it can be represented as alpha and beta. Therefore, the qubit can be written as alpha beta. We can simplify the total qubit with the help of vector and state representation. Then psi is equivalent to alpha and beta. Here, if you want to check the probability conditions, here these alpha and beta are the probability amplitude. If you want to check the normalization condition, you have to check the values like alpha square plus beta square must be equivalent to 1. If this condition is valid, this is the normalization condition. Therefore, this is the vector form of representation psi equivalent to alpha and beta. This condition ensures that the probability must be equal to the 1. Therefore, the measurement and the probabilities, if the psi is equivalent to alpha, beta, if the probability of state 0 is related to the alpha square, the probability of 1 is related to the beta square. After the measurement of all the possibilities or the probabilities, the qubit collapses to the observed state. For example, as mentioned in terms of interference, the favorable probabilities are summing up, unfavorable probabilities are destroying. After measuring these probabilities, if the alpha square value is higher as compared to the beta square, the result is appear related to the state 0. So interference is completely related to the favorable and unfavorable conditions. So the probability sum up related to the favorable point of view. If it is unfavorable, it destroys the probabilities that added to the favorables. So after measurement of all the probabilities, the qubit collapses to the observed state. As till now we discussed about the 1 qubit system. In case of 1 qubit system, the number of states are equivalent to 2 power 1, which is nothing but 2 states that already we discussed about the 0 and 1 state. But whereas how we can represent this quantum qubit mathematically if it has more than 1 qubits. For example, if I take it as 2 qubit, 2 power 2 states, that is nothing but 2 square, which is nothing but 4 states. Those are like state 0 0, comma, state 1 0, comma, state 0 1, comma, state 1 1 states. These are the available 4 states. And in general, it is represented with the psi alpha state 0 0, beta state 1 0, gamma state 0 1, delta state G1 1 states. Here alpha, beta, gamma are the gamma, delta are the probabilities related to the 0 0, 1 0, 0 1, 1 1 respectively. But in the previous case, if you have like a alpha 0 state plus beta 1 state, we can simply replace the 0 with the 1 0 vector and 1 is simply replaced with the 0 1 vector. But here, in what way we can represent the 0 0 mathematically or 1 1 mathematically? So there is a different scenario we have to follow to represent the multiple qubit point of view. So in case of multiple qubit point of view, we use the rule like tensor product to estimate the mathematical values related to the multiple qubit system. So here, for example, 0 tensor product with the 1. Here the 0 and 1. For example, 0 state is related to the 1 0 and here it is related to the 0 1. Now we can take it as 1 0 0, 1 1 1, 0 0 0, 0 1 0. So if you want to represent the 0 and 1, 0 and 1, so the answer is related to the, in case of vector form, 0 1 0 0. Similarly, if you want to take it as like a 0 outer product with the or tensor product with the another 0, we'll take it as 1 0, again 1 0 is related to the 1 1 1, 1 0 0, 0 1 0, 0 0 0. So this is the representation. Similarly, if you want to talk it about like a state 1 tensor product with the another state 1, obviously I need to take it as like 0 1 outer product with the tensor product with the 0 1. So 0 0 0 0 1 0 1 0 0 1 1 1. So by using this, there is a possibility to represent different combination 0 0 1 0 0 0 0 1 0 1 0 1 0 0. Similarly 0 0 0 1. Finally, this all psi is also take it as like alpha, beta, gamma, delta like this, or alpha 0 0, beta 0 1, gamma 1 0, delta 1 1 like this. So this is the combination we use, and finally the probabilities must be equivalent to alpha square, beta square plus gamma square plus delta square must be equivalent to 1. This is a simplified model or the mathematical approach to represent the qubit and the operations among the different qubits point of view. For example, to understand more detail related to this particular problems, express the following qubit states as column vector. Psi is given as 1 by root 2 state 0 plus 1 by root 2 state 1. He is asking about this qubit state should be converted as column vector. Therefore, 1 by root 2 state, this value is taken as 1 0, and this is also 1 by root 2. This I can take it as state 1 0 1. We can write it as like 1 by root 2 0 plus 0 1 by root 2, and it can be represented as 1 by root 2 and 1 by root 2. This is like representation of the column vector. If you want to check whether the given qubit system is normalized or not, then we need to check it as alpha square plus beta square. Here it is the alpha is nothing but 1 by root 2, which is nothing but 1 by 2 plus 1 by 2, which is nothing but 1. So the given problem is the normalized qubit. And coming to the another examples, psi equivalents to 3 by 5 state 0 plus 4 by 5 state 1. Similarly, as like previous, 3 by 5 state 0 is 1 0, 4 by 5 1 is nothing but 0 1. So this finally I just write it as directly 3 by 5 and 4 by 5. This is the alpha and its beta probability amplitude. If you want to get the normalization condition, so 9 by 25, because 3 square by 5 square and 4 square 16 by 25, which is nothing but 25 by 25. So this is related to the 1. So in this way we can represent the whatever the qubits, it can be represented as column